Welcome to Machine Learning and Pattern Recognition. This is a full semester course, about 14 weeks in duration, that will cover the topics of machine learning and statistical pattern recognition. The following lectures are to be supplemented with the books and papers available on Canvas and the slides provided by the instructor. Machine learning and pattern recognition are very broad areas. It is thus impossible for us to cover every topic in detail. In this course, we will present a review of major topics in machine learning and pattern recognition that should be accessible to graduate students and, to a lesser extent, engineers and senior undergrads. We will, however, assume you are familiar with basic concepts in statistics and linear algebra. You should also have taken a course on random variables and, if possible, stochastic processes. At Ohio State, for example, this would correspond to 𝗜희𝘀𝘁𝗿𝘂, which is a course on probability in random variables, and a course maybe such as 𝗜희𝘀𝘀𝗁𝗡𝗡𝗅, which covers optimization for static and dynamic systems. You may also have taken 𝗜희𝘀𝘀𝗁𝗡𝗅, which covers image processing and many of the prerequisites that are necessary for machine learning and pattern recognition. We also recommend you supplement this course with one in convex and non-convex optimization, and perhaps one in estimation theory. We will cover several topics in this class. The major ones are classification, regression, and clustering. But we can subdivide this into a number of important topics in machine learning and pattern recognition, which are the basic concepts and notation that we will use throughout the course. This is going to be covered in the first couple weeks. Then we will turn our attention to generative methods and supervised learning. We will also cover Bayes classifiers and the Bayes error. We will then talk about unsupervised learning, mixture models, and the EM algorithm, to be followed by graphical models and linear regression, statistical learning and kernel methods, nonlinear regression, which includes deep learning, which will be a significant portion of the course, and also the evaluation and comparing classifiers, the evaluation of classifiers and comparing classifiers. Time permitting, we will also talk about transfer learning and other types of machine learning that have become more popular in recent years. We will see that what makes learning difficult is the problem itself. Machine learning, or learning in general, is an ill-posed problem, as shown in this figure on the slide. Given a set of points, shown here in red, there are several underlying functions from which these points could have arisen. It is the problem of machine learning to identify which of these functions is the correct one. Obviously, without prior knowledge, there is no way we could find out which of these two or infinite number of possible functions is the true one, which means that we'll need to make a number of assumptions that will help us address this problem. Now, I have to state at this point that some problems can be solved with well thought out rules, such as expert systems. An expert system is nothing else than a system in which you hard code the rules to be followed by the algorithm. These have been very successful in many problems, especially for problems that humans find very difficult to solve. However, for problems that are seemingly easy to us, we need to define other methods, because expert systems or hard coding of rules does not seem to work for generic problems such as speech recognition, face and object recognition, and action interpretation. In fact, this goes way back to the Greek philosophers. For example, Socrates talked about the relevance of long-term learning. Diogenes also discussed the importance of learning in the human condition, and Plato may have introduced the key idea of mathematical modeling, and including the mathematical modeling of cognition and learning. Descartes and Leibniz, the same Leibniz that co-founded the area of calculus, argued that learning and thought could be reduced to a mechanical engine. This led Babbage to develop the analytical engine in the early 1800s and aided Lovelace to design the first computer algorithms. It did not take long for Lovelace to think about the brain as a computer rather than a mechanical machine, and one's mental ability and sensory perception as the algorithms. In an 1844 letter, Lovelace famously wrote, "I have my hopes, and very distinct ones, of one day getting cerebral phenomena such that I can put them into mathematical equations. In short, a law or laws for the mutual actions of the molecules of the brain, equivalent to the law of gravity. It does not appear to me that cerebral matter needs to be more unmanageable to mathematicians than planetary matters and movements, if they would but be inspected from the right point of view." As you know, Turing extended on this later on. His brilliant mathematical argument showed that any concept that can be described formally, meaning mathematically, can also be executed by a computer. Can learning be reduced to a set of mathematical equations? Well, in the 1950s, the newly created area of artificial intelligence, or AI, set out to prove this was the case. 𝗜ጵ𝘀𝘁𝗁𝗂𝗰𝘁cie and others claim machines would be capable of doing any work humans were doing at the time within 2 or 3 decades, only to discover, of course, that this is not that easy. The problem is that it is very difficult to define what intelligence and artificial intelligence is. In AI, we thought that if we could build algorithms that beat humans at chess, then computers would have to be accepted as intelligent machines. When that was achieved, the problem was changed to Jeopardy. When that second problem was successfully achieved, the problem was changed again to the game of Go, which is a much harder problem to get to master by computers because of the large number of possible options at every single time in the game. Then, when this problem was achieved, the problem became poker. Poker is a game that requires to know whether other players are lying and to learn to lie yourself. This problem has also been solved. Computers can now beat the best players at poker. Again, the problem is we still don't know how to define intelligence. Without a good way to defining intelligence, it is very difficult to determine what are the things that computers should do that are currently able to do now. What we do know is that what's special about humans is our ability to learn almost anything we set out to do. In machine learning, then, we will not program a computer to do a specific task, but rather we will try to learn to do a specific task, much like humans do. The hope, then, is to see if we can build computers that are as good at learning every possible task as humans are. As stated earlier, this is a very difficult problem because many solutions are possible given a certain number of observations, being it when we talk about supervised learning or unsupervised learning. We will discuss all these things in detail. To do that, we will use a number of books. There is unfortunately no single book that is going to cover all the topics that we need to to describe or discuss in the area of machine learning and pattern recognition. Nonetheless, there are several books that are very useful that I'm going to list here. It's not a comprehensive list, but it's a list of the major books that I have used to create this course. The first books that I'm going to show you are very broad books that provide a short but good mathematical introduction to the problem of pattern classification. The first one is called Pattern Classification by Duden and Hart. There's also Fukunaga's Statistical Pattern Recognition, which is a very well and very accessible, very well designed, very well written, and very accessible book on the topic. There's obviously also the book called Machine Learning, A Probabilistic Perspective by 𝗜HIV that I would highly recommend, and I have also used to prepare my notes. And there is another modern book called Pattern Recognition and Machine Learning by Christopher Bishop, which is extraordinary and very complete. Another book that I have used to prepare the lectures is The Elements of Statistical Learning, published by Springer, which has a more statistical view of machine learning. It also has covers many topics in detail that are very useful for people working in this area. Another book in statistics and signal processing that is very useful for what we will see in this course is called A Probabilistic Theory of Pattern Recognition. Highly recommend it as well. We will talk a lot during in the topic of generative methods. We will talk about specific areas of research such as pattern recognition, principal components analysis and independent components analysis. And these are two books that I would highly recommend for this topic. We will then turn into generative methods for classification. And in particular, this is called discriminant analysis. And this is another good book that covers this topic. When we turn our attention to clustering and unsupervised learning, we will talk about finite mixture models and the EM algorithm, which are covered in detail in these two books. Then with regard to graphical models, I'll be using two excellent books. One is called Probabilistic Graphical Models, very recommended book to have in your shelf. And I will also be using Probabilistic Reasoning in Intelligent Systems, which is another fantastic, older but fantastic introduction to the statistics related to graphical models and other statistics that we will be using throughout the course. When we talk about the statistical learning, I'll be using three main books, two by Vapnik. One is called Statistical Learning Theory. The other one is The Nature of a Statistical Learning Theory. And the other book I'll be using is Spline Models for Observational Data. I will also use sporadically a really well-written, very accessible book called Learning from Data that I would highly recommend. There is actually a set of videos available online that cover all the lectures taught at Caltech by the instructor and the writer of this book that I would also recommend if you want to dig deeper into this topic. When we talk about kernel methods, I'll be primarily using this book here, Kernel Methods for Pattern Analysis. For functional data, I will be using a variety of books, including this one, which I think is pretty complete. And when we turn our attention to deep learning, I'll be using a book that was published recently, basically called just Deep Learning. If we have time in the course, I will also talk about combining classifiers, and there's a very good book published in the late 90s, early 2000s, I think, called Combining Pattern Classifiers that does a really great job at introducing all the different techniques. Now, as we said, there are many things that are going to be assumed in this book, such as calculus, linear algebra, and probability and random variables. A number of books that you could use to supplement this machine learning pattern recognition class if you don't have or if you need to review rather these topics would be vector calculus. This is the book I usually follow, which is presents a really easy, really straightforward introduction to calculus. Really clear, very recommended book. Should probably be in all of your shelves as a reference book. Another book that I would highly recommend that you buy or have access to somehow is Matrix Computations. I will be making reference to this book all the time. I describe all the algorithms related to matrix computations that we will be using in this course. Obviously, machine learning and pattern recognition, as we will see and I have mentioned earlier, includes a lot of optimization and especially convex optimization. With regard to convex optimization, this is the book I will be following, and this is the book that is also used in the classes that I have mentioned here at Ohio State. Another book that I really like is this one that talks about many of the topics, the optimization topics that we will cover for linear and convex and non-convex optimization. Very highly recommended book. We will also talk a lot about modern statistics, and this is a good book that describes how to use modern statistics in science and engineering. Also, again, highly recommended. If you want a broader view of artificial intelligence, a good book to have as a supplement to everything that we have discussed thus far is this book on artificial intelligence, A Modern Approach. Another book that you may want to have accessible is Algorithms, because we will be referring to some of the algorithms that are described in this book. And beyond the books that we are going to be using in this course and the books that I just outlined here that are extensions to the course that you may be interested in looking at, there are other books that you could get as general good reads. There are sort of related to what we're doing. They are very accessible. They're books that any engineer should easily be able to read, and highly recommended as something to do on a weekend as a distraction, but something related to what you are learning. The first one I recommend is a Pulitzer Prize book called 𝗜Ð𝘀𝘁𝗁𝗂𝗂. Really good book, really easy read, but really general good book. Another one, which is a classical book by von Neumann that was written many years ago, but basically had a huge influence on artificial intelligence, early days of artificial intelligence and machine learning, is this one here, Theory of Games and Economic Behavior. A modern book that I recommend if you want to buy something published very recently is the book of Why. Again, another excellent read for a weekend. And obviously a classical book from the 1980s is Minsky's The Society of Mind, that talks about artificial intelligence and what artificial intelligence should be. Very relaxed but very profound book on the relevance in the philosophy of artificial intelligence and what intelligence really is. And again, if you prefer a more modern view of the philosophy of artificial intelligence, I would highly recommend Tenet's recent book, From Bacteria to Bach and Back, The Evolution of Mind, which is an excellent book on the philosophy of the mind and artificial intelligence. Another general book I would like to recommend to all graduate students is a book published by or written by Ramon y Cajal, which is called Advice for a Young Investigator. Was written a long time ago, but I think most of what is written, not all, but most of what is written in here is still applicable today, and I hope you find this very useful. All right, welcome to the class again, and we'll start with the topics of machine learning and pattern recognition in our first lecture.